For decades, space has been the final frontier. The recent advancements in propulsion technologies will aid humanity in our quest to explore the far reaches of our solar system. Today, I will go into detail and explain how ion thrusters work and how they will be used in future exploration missions. The main propulsion system used in modern rockets are liquid rocket fuel, solid rocket fuel, and ion thrusters. Liquid-fueled rockets pump a fuel that is either liquid hydrogen or liquid kerosene with an oxidizer into a combustion chamber where burning can occur. Liquid rockets such as the Saturn V in NASA's new Space Launch System require large amounts of fuel to achieve a significant amount of thrust. The Saturn V's engines consume 1,300 gallons of fuel per second in order to achieve liftoff. While liquid rockets are ideal for reaching orbit, they are not efficient enough for deep space travel. Solid rocket propellants are mixed together and then packed into a solid cylinder. The only way to stop thrust is to destroy the casing that houses the propellants. The Space Shuttle and the new Space Launch System both use solid rocket engines to provide additional thrust upon liftoff. Solid rockets are not typically used in deep space because they can only be used once, which would limit the flexibility of missions. Ion propulsion systems ionize propellant and eject charged particles in order to produce thrust. They have high specific impulses, meaning they require significantly less propellant for a mission than would be needed for chemical propulsion systems. They are designed to operate over long durations, accelerating spacecraft over several thousand hours opposed to several minutes. This enables spacecraft to achieve such high velocities using ion thrusters. There are 4 parts to an ion propulsion system. The first is the ion thruster, which I'll get to in a little bit. Second is the power processing unit. The power processing unit converts electrical power from a power source, usually solar cells or a nuclear heat source, into the voltages needed for the ion thruster to operate properly. Next, we have the propellant management system. This system is typically divided into a high-pressure assembly that reduces xenon pressure from the higher storage pressures in the fuel tank to a level that is metered with accuracy for the ion thruster components by a low-pressure assembly. Finally, we have the digital control and interface unit. This unit controls and monitors system performance and performs communication functions with the spacecraft computer. The major components of an ion thruster are its discharge chamber, high-strength magnetic rings that produce a magnetic field, a propellant injector, a discharge cathode, a screen electrode, an accelerator electrode, and a neutralizer. In order to ionize the propellant injector and discharge cathode release neutral atoms and electrons into the discharge chamber. A neutral atom will collide with an electron, which causes ionization to occur. During the collision, the atom loses one of its electrons and becomes a positive ion. The ions are accelerated by a high voltage from the accelerator electrode. The positive ions are propelled out of the thruster at speeds up to 90,000 miles per hour. As the ions are propelled out of the thruster, the neutralizer releases an equal amount of electrons to make the total charge of the exhaust beam neutral. Without the neutralizer, the spacecraft would build up a negative charge and ions would be drawn back to the spacecraft, which would reduce thrust and cause erosion. NSTAR, or NASA Solar Technology Application Readiness Engine, was designed to operate over a 0.5 kilowatt to 2.5 kilowatt input power range. NSTAR's primary propellant is xenon. Xenon is a popular fuel propellant because it is easily ionized and has a high atomic mass. The thruster uses xenon to produce between 19 millinewtons to 92 millinewtons of thrust. These thrust values are comparable to the weight of a sheet of paper. The thrust values may seem small, however, they are relatively large with respect to the mass of the ion particles. NSTAR was used on the Deep Space One mission and on the Dawn spacecraft. The NSTAR on Deep Space One was able to accumulate over 6,600 hours of thrusting while only using 30 kilograms of fuel to reach a speed of 10,070 miles per hour. The Dawn spacecraft had 3 NSTAR engines and became the first spacecraft in history to orbit 2 extraterrestrial destinations, Vesta and Ceres. NASA is currently developing the next generation of ion thrusters. Its new thruster will be called NEXT, or NASA Evolutionary Xenon Thruster. NEXT is designed to operate over a 7 kilowatt power range and have 3 times the power level of NSTAR. These new innovations will reduce mission cost and trip time. NEXT and future ion thrusters will open a new era of space exploration. Probes will be sent on missions that were once thought to be impossible. The The future is bright and the time for discovery is now. I hope you enjoyed learning about ion thrusters, and as always, thanks for watching.